I don't know why. Let me double check what's happening here. Guys, could you please check for me if you're able to unmute yourself?
I can.
Okay, awesome, awesome. Sorry, I was playing around with the settings without knowing. Okay. Now, before we said that if you displace a structure according to a mode of vibration, then the shape of the motion will remain over time. The structure will be displacing following an harmonic deformation, okay? So this is happening here. The structure is displaced according to mode 1. This is mode 1. Why is mode 1? Well, because in this case, this is a shear type building and I don't have nodes. Because I don't have nodes, then this must be mode 1. Remembering that the number of nodes is equal to the mode number minus 1. Because I don't have nodes, this is mode 1, okay? In mode 1 is very easy to remember in case of shear type building. Well, because in this case, the displacement is always positive or always negative. I don't have nodes, okay? And again, the shape of the motion is harmonic. When I go through a minimum, I go through a minimum at both levels, level 1 and level 2. When the displacement is reaching the peak value, this is happening at level 1 and level 2. And I remember that this motion is harmonic. Now, we said before that a mode shape is only the shape of the motion. The shape is the same, but the amplitude can change. The motion is always proportional to the mode shape, but the amplitude of the motion can change, okay? So what I can do is the following. Imagine that I know how to find these mode shapes. We will learn how to find them later on. Imagine that I know how to find them. Well, I understand that only the shape of the motion is important. Only the shape of the motion is important. So for instance, for level 1, I can find this value of displacement. For level 2, I can find this value of displacement, which is defining the shape of the motion. Only the shape is relevant, because I understand that over time, if I know the amplitude of this shape, if I know the displacement, the modal displacement at level 1 and the modal displacement at level 2 for mode 1, and if I can write these two in a vector, which is here, okay? Well then, if I want to find the time history of the displacement of these two masses over time, well, all I need to do is to multiply the mode shape times a function which is changing with time, okay? This function which is changing with time is called modal coordinates. So if I know the mode shape for mode 1, and I want to find the displacement of these two masses according to mode 1 over time, well, all I need to do is to multiply the mode shape times the modal coordinates. Well, how is the function of the modal coordinate going to look like? Well, I understand that this is a free vibration response, and therefore it must be similar to the free vibration response which we have studied for single degree of freedom system. So for single degree of freedom system, the law for free vibration response was written as an cosine omega n t plus bn sine omega n t. Okay? I understand that this is only a value which is changing with time, which is now multiplying a vector to obtain what? To obtain the vector of the displacement containing the displacement of this floor and the displacement of the floor above according to mode shape number 1. And therefore, what I can say is the following. The displacement of these nodes according to a mode shape is proportional to the mode shape, okay, which is a vector, times the modal coordinates. The equation for the modal coordinates must be similar to the equation for a single degree of freedom system under free vibration. As for the single degree of freedom system, these constants, which are an and bn, well, they must be obtained starting from the initial condition. Okay? Guys, is this clear, yes or no? Let me ask you. Is this clear, yes or no? Meaning, you know, do we all understand what a mode shape is? Yes or no? Okay. Well, if this is the case, the same equation can be written remembering that the displacement un is basically now a vector, where I have the displacement of level 1 and then the displacement of level 2. Then what I want to do is to find these modal displacements, which are also called the mode shapes. I want to find this vector, which is the vector of the mode shapes, and then I need to multiply times the modal coordinates. The modal coordinate, we understand, that must be an cosine omega nt plus b sine omega nt, which is also the solution for a single degree of freedom system under free vibration. But now, why do I have n here? Well, clearly because these constants, a and b, will be different depending on the mode number. So for mode 1, I will have some constants. For mode 2, I will have other constants, and so on. Same story for omega n. Now, this is now the frequency of mode 1, for instance, or mode 2, and so on. Okay? Well, I can derive this equation to obtain the acceleration. The acceleration must be proportional to the mode shape. The mode shape is not changing when I derive. What's happening is that as for the single degree of freedom system, this will be now the derivative to obtain the acceleration. And therefore, I can now replace this result into the equation of motion. The equation of motion is the stiffness matrix times the displacement vector plus the mass matrix times the acceleration vector is equal to 0. All I need to do is to replace this result for the acceleration and this result for the displacement in the equation of motion. And now I have the stiffness matrix times the displacement minus omega n squared times the mass matrix times the acceleration, which is written here. This is the same procedure that we have followed for the single degree of freedom system. The only difference now is that this k is now a matrix, u is now a vector, m is now the matrix, u double dot is now a vector. The procedure is the same that we followed for the single degree of freedom system. And therefore, this equation can be rewritten in the following way. Can be rewritten as the stiffness matrix minus omega n squared times the mass matrix, which multiplies the mode shape vectors, is equal to 0, Well, clearly, a solution of this problem is possible if the determinant of the matrix stiffness matrix minus omega n squared times the mass matrix is equal to 0, okay? So a solution is possible if the determinant of this matrix, which is written here, is equal to 0. Now, clearly, you understand that if I write the determinant of this matrix, I will get a polynomial equation. The roots of the polynomial equations are the frequencies of vibration of a multi-degree of freedom system. We will see that in a minute. So, do you understand that this problem, meaning finding that the determinant of this matrix is equal to 0, will be a polynomial equation, which is also called the frequency equation. It's called the frequency equation because the roots of this equation will be the natural frequency of each mode of vibration. Well, you understand as well that this is the eigenvalue equation of the problem, while the eigenvector equation and basically the modes of vibration can be obtained by replacing these values, the frequency values, into this problem. After I have the frequency values and I plug in the frequency values into this problem, I can obtain the mode shapes of my multi-degree of freedom system, okay? So from this equation, I will get the frequencies of vibration. From this equation instead, I will get the modes of vibration. So the first step is that of writing this equation for your multi-degree of freedom system, from which you can obtain the frequency of the system, the frequencies of vibration of the system, and then one at a time, you will plug in that result into this equation to obtain the modes of vibration. We will see how to perform this operation in a minute, okay? Now, let's consider, for instance, the system that we are investigating is this system. This is a 2-degree of freedom system where the mass at level 1 is 2m, the mass at level 2 is m. The stiffness at level 1 is 2k, the stiffness at level 2 is k, okay? Well, we say that the problem of free vibration can be written in a simple way. It's simply equal to the mass matrix times the acceleration vector plus the stiffness matrix times the displacement vector is equal to 0. This is the problem of free vibration. Let's try to write these equations together. Well, I understand that mass matrix is very easy to write. All I need to do is to write this mass to m and then the mass at the level above on the diagonal. And why on the diagonal? Well, because this is a shear type building, meaning in this case, as we have seen before, I can write the mass matrix simply by listing the values of the masses starting from the ground level and moving up to the roof of the structure. In the same way, I can write the acceleration vector. This is u double dot 1 and this is u double dot 2, okay? Now what I need to do is to write the stiffness matrix of the system. To write the stiffness matrix of the system, as we have seen before, what I need to do is to apply a unit displacement at this level. So the unit displacement will now produce a deformation which is similar to the one that I'm showing. And then what I need to do is to find the reactions at the pins which are needed to keep the structure in this deformed shape. At level 1, well, the reaction is going to be proportional to 2k plus k. So it's going to be equal to 3k, basically, okay? Level 2, the reaction is going to be proportional to k and is pointing in the opposite direction. And therefore, it's minus k, okay? So this level is 3k, at this level is minus k. These are the values of the stiffness matrix for the first column of the stiffness matrix. Let's go and write them down. So the mass matrix is here. The stiffness matrix, we say it is 3k minus k. When now I apply a unit displacement at the level above, the deformed configuration will be the following. At this level, the stiffness is going to be equal to minus k, meaning the reaction that I need to apply to keep this deformed configuration is minus k. The reaction that I need to apply now at this level is k, and therefore the stiffness matrix is minus k, k, okay? Well, then I now have the mass matrix, I now have the stiffness matrix. So if I write the determinant of the stiffness matrix minus omega n squared times the mass matrix, if you perform this operation, write the determinant of this matrix, you will have a polynomial equation, which is written here. The roots of these polynomial equations will be the natural frequencies of the system. So I will have two natural frequencies because this is a 2-degree of freedom system, and these two natural frequencies are written here, okay? Well, you remember that the period of vibration of mode 1 will be larger than the period of vibration of mode 2, okay? Therefore, the frequency of vibration of mode 1 will be smaller than the frequency of vibration of mode 2. So these are the results that I obtained for the frequency of mode 1 and for the frequency of mode 2. These are also called the eigenvalues of this problem. How do I find the eigenvectors? Well, what I need to do now is to plug in these results into these equations one at a time. So let's do that on the following slide. We say that the first mode is written here, the frequency of the first mode is written here, the frequency of the second mode is written here. So if I plug in this result in this equation, well, then I can find mode shape number 1. When I'll be plugging in the frequency of mode 2, then I will be obtaining mode shape number 2. Because we understand that this is only a mode shape, meaning, it's a shape of the deformation, the actual values in this vector are not important. What's important is the proportion between these two values, because this is only, a shape in which the deformation according to mode 1 is happening. Well, because this is the case, when solving this problem, I can set the displacement of the roof to 1 for both modes. Because, the actual values of these displacements, of these modal displacements, are not important. What's important is simply the deformed shape, meaning, the relative, basically the ratio between these different displacements. And therefore, I can plot mode 1, which is plotted here, and I can plot mode 2, which is given here. Okay, so we were able to obtain the first mode of vibration and the second mode of vibration. So again, what is a mode of vibration? A mode of vibration is a special deformed shape of the structure. And if I deform my structure according to this mode of vibration, well, the shape of the motion will be remaining over time. The motion is going to be harmonic. The masses are going to hit the maximum displacement at the same time and the minimum displacement at the same time. Also, I can define the frequency of vibration. The frequency of vibration can be obtained for the first mode and for the second mode, following the procedure that we've seen. Guys, before I move forward, let me ask you, is this clear? Do you have questions, any of you? Let me ask you. Let me try with this tool. Okay. Therefore, let's move forward. Well, the following problem is very much the same problem. All it's changing now is that I have 3 degrees of freedom. 3 degrees of freedom. Well, if this is the case, what I need to do is simply list the mass values starting from level 1. So I need to move up in my structure, and I need to list the mass values to form the mass matrix. So in this case, I will have 0.35, 0.263, 0.175, okay? Well, when it comes to the stiffness matrix must be obtained following the same procedure that we've seen before. So what is the procedure that we've seen before? Well, imagine that I need to obtain the second column of this matrix. I want to obtain the second column. So this is level 1. This is level 1, this is level 2, this is level 3. Imagine that I need to obtain the second column. Well, what I need to do is to apply a unit displacement at this level and restrain the other levels with pins. Therefore, the deformed shape of the structure will be now the following, okay? Well, How big is the reaction at this level? Well, clearly the reaction at this level is going to be negative. This spin must be applying a reaction in the negative direction, which is proportional to K2, and therefore is minus 210. How about the reaction at this level? Well, the reaction must be pointing in the positive direction. How big is this reaction? It's 210 plus 105, which is 315. How about at the roof level? Well, at the roof level, the reaction must be pointing in the negative direction. How big is this reaction? Well, it's minus 105, which is written here. Well, in the same way, you could be obtaining the first column and the second column. To verify that this matrix is correct, well, you need to know that the elements along the diagonal are positive, and also that there is symmetry in this matrix, okay? So this is how the stiffness matrix is obtained. Now, what I need to do is obtain the frequencies of vibration of the system. How do I obtain the frequencies of vibration of the system? Well, I need to write that the determinant of this matrix, is equal to 0. When I write that the determinant of this matrix here is equal to 0, because this is a system of equation which will have a solution if the determinant of this matrix is equal to 0, the result of writing the determinant of this matrix equal to 0 is a polynomial function, and the roots of these polynomial functions will be the eigenvalues of this problem or the periods of vibration of this problem, the frequencies of vibration of this problem. Well, in general, there are tools available to you which you can use to find these eigenvalues. For instance, if you Google Wolfram Alpha, online this tool is available for free. What you can do is to write this matrix, press enter, write eigenvalues of the matrix for which you need to find the eigenvalues, and the software is going to give you the polynomial equation. Then, if you press enter one more time, the software is going to plot for you the equation, and is going to give you the roots of the equation. The roots of the equations are the frequencies of vibration of the system, okay? The frequency corresponding to mode 1 will be the smallest frequency. So omega 1 will be smaller than omega 2, will be smaller than omega 3. And you will write them in order. And of course, you could be computing as well the corresponding periods of vibration. In this case, the period of mode 1 will be the largest. In this case, it's 0.58. The period of mode 2 is 0.18. The period of mode 3 is 0.10. Now, you have the eigenvalues of the problem. What you can do is to start from mode 1 to obtain the first mode shape of the system. And therefore, what you need to do is to plug in this value into this system of equation to obtain phi1, the first mode of vibration of the system. If you perform this procedure for the different mode shapes, this is the result that you will be obtaining. And as before, you can set one of the degrees of freedoms to 1. So for instance, in this case, we are setting the degree of freedom, these degrees of freedom, to 1. We are doing that because only the shape of the deformation is important, not the absolute value. Only the shape of the deformation is important. And then clearly you can write all these results in Excel. So for instance, you will be writing the mass at the different levels, you will be writing the periods of vibrations, you will be writing as well the mode shapes, okay? Where the displacement of the roof of the structure is set to 1 for mode shape 1, for mode shape 2 and 3. And this is because, the actual values are not important, but it's only important the ratio between these values, only the shape of the deformed shape. Okay, guys, before I move forward, do you have questions regarding how, to obtain modes of vibrations and periods of vibration for a multi-degree of freedom system? Is this clear? Okay. Well, if this is clear, we are, very much to the end of this presentation. And, the concept that we will see right now is very important. It's very important because we understand that in the problem we were trying to solve before, which is written here. Let me try to go back. In this problem, which is written here for a 2 degree of freedom system, okay? Well, I have two equations of equilibrium. One equation for level 1, another equation for level 2. These equations of equilibrium, in this very moment, are coupled equations of equilibrium, meaning, they cannot be solved independently. As of now, in this equation, I have variable 1 and variable 2. They cannot be solved independently. I have two equations and two variables. This is a system of equations. The system of equation is a coupled system of equation, meaning, in both equations, I see U1 and U2, okay? And this is coupled through the stiffness matrix. The coupling, in this case, is due to the stiffness matrix. But, now we were able to obtain the modes of vibration. Therefore, what we can do is to use another result, which I'm about to explain. Okay. Another result that we will be using is the result due to the orthogonality of modes. What is the orthogonality of modes? Well, the modes of vibration are orthogonal with respect to the stiffness matrix and the mass matrix. Meaning, if I write that the transpose of a generic mode shape times the stiffness matrix times the mode shape R, okay, I will get 0. The same applies if I perform the same operation using the mass matrix. So if I consider two generic mode shapes, N and R, and I perform these operations, I will get as result 0. Okay? We will say that the mode shapes are orthogonal with respect to the stiffness matrix and the mass matrix. How can we demonstrate this definition, if you wish? And also, which are the implications of this demonstration? Well, the demonstration is very easy. What I need to do is to pre-multiply. I know that the stiffness matrix times the mode shape is equal to what? Is equal to omega n squared times the mass matrix times the mode shape. Okay? Well, how do I know that? Well, it's written here. It's written here. So all I did here was basically to write that we know that K minus omega n squared times the mass matrix times phi, which is the mode shape vector, is equal to 0. And therefore, this can be written as K, the mass matrix, times the mode shape vector is equal to minus omega n squared times the mass matrix, okay? Now, what I can do is to pre-multiply this equation times the transpose of a different mode shape. So this, if this is n, I pre-multiply this equation times the transpose of a different mode shape. Let's call this different mode shape R, and I do the same here. Okay. Well, I can perform the same operation for mode shape R. So in this case, I pre-multiply times the transpose of mode shape N. So I have two equations. one was obtained for mode shape N, the other one was obtained for mode shape R. We have equation 1 and equation 2. Now I can perform the operation equation 1 minus equation 2. If I perform this operation, this is the result that I get, which is showing that now if I perform the operation Phi transposed times the mass matrix times Phi R, where N and R are two different mode shapes, then the result is equal to 0, meaning the mode shapes are orthogonal with respect to the mass matrix. Well, the same result can be obtained for the stiffness matrix. So I can obtain that the transpose of the mode shape N times the stiffness matrix times mode shape R is equal to 0, where N and R are two generic mode shapes. The same result can be obtained for the mass matrix. Okay? Well, it's clear then that I will be obtaining another stiffness matrix, which is different compared to the previous matrix which we wrote before. And this stiffness matrix is obtained by performing the operation the transpose of the mode shape times the stiffness matrix times the mode shape. I understand that in this case, this matrix will be a diagonal matrix because all the terms outside the diagonal, meaning all those terms for which N and R are two different numbers, will be equal to 0. The same is true for a new mass matrix, which I can be defining in this way. In this new mass matrix, the mass matrix is obtained as transposed of the mode vector times the mass matrix times the mode shape. Well, in this case, this matrix is going to be diagonal as well. And why is that? Well, because for all the terms which are outside the diagonal, meaning for all those terms for which N and R are two different numbers, I will be getting a value of 0. Okay? So only the terms on the diagonal are different from 0. Well, this is a strong implication because right now we were able to obtain two new matrices, okay? One which is defined in this way, the other one which is defined in this way, for which now the problem is a decoupled problem, meaning, now I only have the diagonal terms on the stiffness matrix and on the mass matrix. So if I use these values to define my stiffness matrix and to define my mass matrix, then the system of equation I'm dealing with is a decoupled system of equation, meaning, the equations are not coupled anymore. These diagonals are, these matrices are both diagonal matrices. So let me try to, explain in a different way what I mean. If I define the stiffness matrix and the mass matrix in this way, meaning if I define them after I find the modes of vibration and I write them in this way, and if I define the mass matrix in this way after I find the modes of vibration, okay, if I perform these operations, then my problem will be the same problem that I had before, meaning the stiffness matrix times the displacement vector plus the mass matrix times the acceleration vector is equal to 0. But in this case, both the stiffness matrix and the mass matrix, which can be written in this way, are now diagonal matrices, meaning now, instead of having n coupled equations of equilibrium, I have n uncoupled equations of equilibrium. Meaning, there is no coupling anymore. In each of these equations, in equation 1, my only variable will be u1. In equation 2, My only variable will be U2, and so on. These equations are now uncoupled. It's not a coupled system of equations, but it's an uncoupled system of n ordinary differential equations. In other words, instead of solving a system of equations, I now need to solve n ordinary differential equations. So I now need to solve n single degree of freedom system, where the mass of each of these single degree of freedom system will have this value, where the stiffness of each of these single degree of freedom system will have this value. Okay, so you know, a modal analysis is a very powerful tool. It's a very powerful tool because instead of solving a system of n differential equations, I will end up with solving n single degree of freedom system, meaning n differential equations in which the mass is defined in this way and the stiffness is defined in this way. This operation is called the decoupling of the equations of motion. Guys, is this clear? Yes or no? This was all for today. Let me only ask you, is this clear? Yes or no? Okay. So let's go, you know, the problem which is assigned is a very simple problem. It's basically performing a modal analysis for a simple structure. But let's try to go very briefly on what we have done for today. So for today, so before I go over this concept one more time, let me ask you something. Did you see these concepts already in other classes? So option 1 is yes. Option 2, no, not at all. Option 3, maybe only a part of these topics. Okay, so it seems that you have seen these topics in other classes. So this will help me as well with describing these topics. So what we've done for today was to understand how the modes of vibration and the frequency of vibration can be obtained for a multi-degree of freedom system. Okay, well, clearly we understand that this procedure is only applicable to a linear system. These results are not valid for non-linear system. Okay, so first of all, we understand that the equation of motion can be written as we have seen before for single degree of freedom system, where now this is a matrix, this is a vector. Why is this a matrix and this is a vector? Well, simply because I now have multiple masses for which I need to write the equations of equilibrium. The assumption that we are considering is that of a shear type building, where these masses are rigid, the beams are rigid, and only the columns can deform in bending only, not under axial deformation. So if this is the case, the equation of motion that I need to write is here. And I can obtain the equations of equilibrium using the D'Alembert principle, meaning I need to sketch the free body diagram for the mass of the roof, I need to sketch the free body diagram for the mass below, and the equations of equilibrium will become what is written here clearly. They can be rearranged in a different format, where now I have a mass matrix and a stiffness matrix. The mass matrix will be diagonal. The stiffness matrix is offering coupling to this system of equations, meaning for equation 1, I will have both variable. For equation 2, in this case, I will have both variables. If I need to solve this problem right now, I need to solve n equations of equilibrium simultaneously, meaning it's a system of equations. These equations are coupled. Well, clearly this is not ideal because I need to solve a coupled system of n differential equations. Well, we have seen how to write the mass matrix and how to write the stiffness matrix. And then we have seen how to perform a modal analysis and what is the meaning of a mode shape. So what is the meaning of a mode shape? Well, a mode shape is a deformed configuration of the structure. It's a special deformed configuration of the structure. If I deform the structure according to a mode shape and then I release it, the structure will keep the mode shape, will keep on deforming following the mode shape. In addition to that, when one floor is reaching the maximum deformation, all the other floors are reaching the maximum deformation. When one floor is going to zero, all the other floors are going to zero. In this case, if the structure is in free vibration after it's deformed according to a mode shape, the motion is going to be an harmonic motion, okay? And in this case as well, I can define what is the period of vibration. But how do I obtain the mode shape and the period of vibration? Well, the problem that I need to solve is written here. It's written here, okay? To obtain the frequencies of vibration, I need to write that the determinant of this matrix is equal to 0. If I write this problem, I will have a linear equation, a polynomial equation. The roots of these polynomial equations will be the frequencies of vibration. These are also the eigenvalues of this problem. After I obtain the eigenvalues of the problem, I can obtain the eigenvectors. How do I obtain the eigenvectors? Well, I obtain the frequency of vibrations from the polynomial equation. Then I plug in these results one at a time into this equation to get the mode shapes. This is part of the two problems we have seen together. The very last result, which we have seen for today, and it's a very important result, is the result described in this slide here, which is basically showing that a new stiffness matrix can be written and a new mass matrix can be written, where these two are now diagonal matrix. They are now diagonal matrix because of the orthogonality of the mode shapes with respect to the stiffness matrix and the mass matrix. It's very important that this new matrix I'm able to obtain for the stiffness and this new matrix that I can obtain for the mass are diagonal matrices, because in this case I understand that the equations of equilibrium can be decoupled, meaning if I use these two, because I will have only terms along the diagonal, I don't need to solve a system of equations. All I need to solve is n differential equations. These n differential equations are the equations of motion of a single degree of freedom system for which the stiffness is obtained in this way, for which the mass is obtained in this way. So again, this is a way of simplifying the problem, of rewriting a new value of the stiffness, which has nothing to do with the stiffness of the structure, and the new mass, which has nothing to do with the mass of the structure, but are simply tools to obtain decoupled equations of motion, okay? Which will allow me to solve n single degree of freedom system instead of coupled differential equations. Okay, guys, this is all for today. The assignment is written here, and only a reminder, this will not be part of the midterm, because the midterm is only in 1 week. You have a study guide, which is already posted online, and it's covering the topics that we've seen so far. Okay, so this was all for today. Do you have questions? Anybody?
Professor, I see this homework's due April 7th. That's after spring break, so I appreciate that.
Okay, well, you know, I need to be honest with you. At this time of the day, I'm tired, so I feel for you. I mean, for me, I need to say it's complex to be connected, to keep my brain engaged. So I'm assuming it's the same for you. I mean, and because of that, you know, the study guide is there. I'm hoping it's going to help, and also the assignment is due after the break. Okay, guys, questions? Anybody else?
I had a question for the
Mhm.
homework we had due tonight.
Yes.
Wanted to know if you can go over an overview for the homework.
Mhm. Well, the overview for the homework, I don't know